Okay, so the answers to the homework, we're going to go over them. Obviously, it's what we got here. The first couple questions, as you already know, because I'm sure you did all of the problems, were actually redox reactions. You know what? I've just realized a couple of you all were absent last class. Let me pause. And that's how I saved that person's life. So we're going to go over the answers to these. I just have the answers straight up written in there for some of them. But I thought maybe you would want a review on how to balance redox reactions. I love the fact that you want that. There's a pencil sharpener in the back. That's where we kept it all year. Right. It's electric. Boogie, woogie, woogie. So, in the box, I have the final answer. I left this blank so I could show you the work. Cool? So, first step in a redox reaction is you look at it and you say, oh crap, that's a redox reaction. Right? And that's step one. How do I realize that's a redox reaction? Yeah, now's a good time to sharpen your pencil because there wasn't anything going on a little while ago. Is you look at both sides of the reaction and you say, where did that oxygen go? Oh no, right? Oxygen just disappeared. So you have to approach it from this like multi-step process. The first step I've done for you, which is split the reaction into two pieces. There's an iodine portion and a chlorine portion, and we ignore the other elements initially. And then we're going to slowly go through the 17-step process. I can't remember how many steps. I do them all in my head. But the first step was, if it's not oxygen or hydrogen, try to make them balanced. Is iodine balanced? No. I should multiply this one by 3. Now I have 3 iodines and 3 iodines. Are the chlorines balanced? Yes. So that's the first step in every redox reaction. That's the second step. The first step is actually split them in half and then balance the elements that aren't oxygen and hydrogen. The next step is, now let's fix the oxygens. Are the oxygens in the iodine reaction equal on both sides? How many oxygens are on the left? 0. How many oxygens are on the right? Ergo, they're balanced, right? In the second reaction, oxygens on the left, oxygens on the right, not balanced. So the way we dealt with this is we added water and we rationalized this addition of water because these are all aqueous reactions. So there is definitely water there. We just weren't using them in the past, and now we are using the water molecules to help facilitate the balancing. Have I balanced the oxygens? Now it's time to balance the hydrogens. Back to the iodine. How many hydrogens as a reactant? None. How many hydrogens as a product? Balanced? Woohoo! We do need to fix it in the chlorine reaction. We have 2 hydrogens, and on this side we have none. So we say plus 2 hydrogen ions. Or if that was a Bronsted-Lowry question, we'd say 2 protons. But just call them hydrogens to simplify it. So we have 2 hydrogen ions as reactants, water molecule as a product. And then we did the part no one liked, the charges. Remember that? You'd have to look at the number of charges and try to figure out how many electrons to throw in there. So here we have a -1 on the iodine, which we're multiplying by 3. That would also be known as -3, which I'm just going to use orange. Yeah. So I've got a -3 charge. On the other side, though, I only have one of these things, don't I? This thing is occurring how many times? So that is only a -1 charge. Are the two sides equal in charge? So there need to be some electrons on this side to make the, look at the hiccups, and I'm recording. So how many electrons need to be on this side, the product side, to make it equal? 2. because that would be 2 negatives and 1 negative, which would equal the 3 negatives. So the iodine now has an equal charge on both sides. What are we saying just happened? We're saying that these 3 iodines released 2 electrons, didn't we? These 3 iodines released 2 electrons, and they made a compound called a molecule called triiodide, which is a highly volatile molecule that explodes on contact. It's pretty cool. You just go boop, and it goes boom, and it explodes. We're not allowed to make it, sorry. Next reaction. Again, the charge. What is the charge of this molecule? -1. All right, -1. The charge of this hydrogen, but there's 2 of them, +2. Woo. Oh, wait, just a second. And then over here we have a chlorine with a -1. And what's the charge of the water molecule? 0. Are the 2 sides equal? No. Which side should we add electrons to? If we add a -2 over here, we'd have -2 and +2 and -1, which would equal -1. So this needs to have dose electrons. Here's another reason the electrons have to be on this side. In this reaction, the electrons are on the product side. So in the other reaction, they have to be a reactant. They have to have electrons on the opposite side. One reaction is producing electrons or losing them. This is the losing reaction. If it's losing electrons, we say that iodine is being oxidized. There, you can't see that at home, but they made the noise OX with their mouths. Yeah, and Asha, she made like a big O and then crossed her arms as an X. It was really weird. Yes, she did. And then in this one, it's taking the electrons in, so this is the reduction reaction. Usually there was at this point another step. We don't have to do it this time, but I'm going to remind you. If the electrons were not equal, say this was 6 electrons and this was only 4 electrons, we'd have to get them to equal by multiplying the reactions so that they'd have the same number of electrons. We'd multiply this in the first reaction by some number, the second reaction by some number, so the electron total was equal. Are they already equal though? Let's multiply them both by 1 and we're done. True? So since the electrons are equal and everything is balanced, we can just add them back together, and that's where this equation came from. You add it back together and you got that. Cool? These electrons and these electrons are equal and opposite, so they cancel out. Good question. The requester of the video wanted to know where this and these cancel each other out. Since they're on opposite sides of the reaction, as they get summed back together, they cancel out. Cool? Someone knock on the door? Oh, okay. Click, click. Let's do one more. And the next couple, I'm not going to go through all the steps. I'm just going to give you the answers. You can try to practice them or not practice them on your own time. So I went ahead and I did the easy part. I split it apart into the 2 reactions. When I split them apart, I'm ignoring the oxygens and the hydrogens. I'm just looking at the other elements. What is AS? And then N is, of course, no, that's nitrogen. I was going to say nobelium. That's NB. So step 1, split them apart. I'm sorry, step 1, cry because it's a redox reaction. Step 2, split them apart. Step 3, are the elements balanced? The non-hydrogen and oxygen elements balanced in both reactions. Which one's not balanced? This one, the nitrogen, is balanced on both sides. What about the arsenic? 2 arsenics. Dang nabbit. So, multiply this by 2. Alrighty. Now I've got to go to the other 2 elements, oxygen and hydrogen. How many oxygens are here versus how many oxygens are here? This is 3. That's 8. So I'm going to have to add water on this side How many waters do I need to get the oxygens equal? 5. Because that would be 5 oxygens and 3 oxygens add together to make 8 oxygens. True, Dad? Slightly annoying, but true. Now we're going to do the hydrogens for that reaction. Here, how many do we have? 10. They're complaining about fictitious noises. And 6. 10 does not equal 6, so there need to be 4 hydrogens here also, if I did my math correctly, to make the two sides have the same number of hydrogens. Good? Such a pleasant clicking. Everyone enjoys it. Then let's do the charge for this one. What's the total charge of all of these things on this side? 0 plus 5 times 0 is 0. And then the total charge on the other side, plus 4. True? So I'm going to add 4 electrons on this side. And I ran out of space, so I wrote it underneath. Sorry about that. These 4 electrons will bring the total charge of the products down to 0. And now the charges are equal on both sides. Now let's do the nitrogen reaction. Nitrogens are equal, oxygens are not. Add some water. H2O here. I think I'm adding 2 H2Os. 3 oxygens. Yep, 3. And then 4 hydrogens. Charge is not too bad on this side. This side is a pretty easy charge. That's a 0, right? Hiccups are optional step. You can skip that one. On the other side, though, what's the total charge for this side? 4 times 1 plus 1. But that's a negative one, isn't it? 3. So this is a minus 3, and this is a 0. That's a, thank God, I was having a panic attack. Did you see like the broken gears in my head like sliding apart? Because I was like, if that's a minus 3, I need to add the electrons over here. Oh no, I started the electron. What did I do wrong? Sign. So yeah, that's a plus 3 right there, and therefore I have to add 3 electrons on this side, of course. And now the charge is balanced. Ooh, that's a big eraser. How do I get the electrons to both be the same value? Oh, my knee just popped. What should I multiply them by? First reaction is going to get multiplied by... Did you say 8? 3. Oh, that makes way more sense. The home audience, that's really just for the home audience amusement. I know you said 17. And I'm going to multiply this one by 4. And then when you sum them back together, some of the stuff does cancel. 4 times 4 is 16 hydrogens. Over here you have 3 times 4, so 12 hydrogens. If you have 16 hydrogens and 12 hydrogens, how many hydrogens actually reacted? Yeah. Which is where that 4 hydrogens came from in the answer. Same thing kind of happens with the water. Some of the waters cancel out, but the basic pieces are okay. Where did this 3 come from on the diarsenic trioxide? We multiplied everything by 3. Everything in there got multiplied by 3. I can tell by your enthusiastic faces you're really glad to see redox reactions back. Right? Yeah. Your enthusiasm reminds me of flu season right now. I'm not going to lie. No? Okay. Thank you for the smile. Like, yeah. Here's 2 more answers that I'm not going over the steps for. Feel free to try to go through those steps and try to get to the correct answers. I don't know why that charge is above the box. I ran out of box space, so the H2O leaked out the side, which was kind of funny. I got a giggle from one person and a direct, like, just a wrath. Oh, okay. You're allowed to shake your head like that at her. That's fine. Oh, that's not what I thought it was. Uh-oh. There. Oh, I almost got it back in the box. All right. Number 2. We've gotten all the way to question 2. That's exciting. Balance the following oxidation reduction reactions that occur in a basic solution. It's like it was a refreshing noise. So you go through all the steps, and I did this with B here. You go through all the steps, and you get to this point. Ta-da! Yay, I'm balanced. But what evidence in that purple blob I just drew is that the solution is acidic, not basic? It's got free hydrogen ions. What's another name for hydrogen ions? Proton. A proton. Hydronium's H3O. And so if it's a basic solution, we need to neutralize those 4 hydrogens with 4 hydroxides. But we just went through this process of carefully balancing it. So we add 4 hydroxides to both sides. If I add 4 OHs and 4 OHs, the totals are still the same. What happens when these 4 hydrogens and these 4 dang it, I skipped to the answer. Maybe you didn't hear it. They did hurt. Yeah, these guys here, or girls, are coming together to make 4 waters. And then these 4 waters and these 2 waters are going to kind of reduce down a smidge. So that's what I did with A and C. Also, actually with A, there was no leftover hydrogen. And if there's no leftover hydrogen, how much hydroxide do I need to add? You have no hydrogens on one side and no hydrogens on the other side. How many hydroxides do you need to add to neutralize the hydrogen? None, right. If there's no hydrogens, you add no hydroxides because it's already balanced without it. And then that one also. Oh, man. I did something to my knee a second ago. And so this is actually pretty easy to do, isn't it? Okay. Just messing with you all at home. Okay. Number 3. Number 3 is where we're going to finally get into some new stuff. Not old new stuff, like I've forgotten how to balance a redox reaction, but like the new stuff mixed in with the old. Right here, it clearly says, use a table of standard reduction potentials. If you look in your textbook, you will see multiple pages of these reactions. And then at the end of the reaction, it says, here's the voltage for that reaction. That's what they're referring to. Look at a data table to find the voltage. Now, on our test, on the AP exam, those things are given to you. Given to you for that equation. You do have to figure out what to do with them. When you look up the iodine reaction, it is not written this way. The iodine reaction is written I2 plus 2 electrons produces 2I minus, and then it says positive 0.54. So what did I have to do with that reaction before I could use it? I had to flip it. When you flip the reaction around, what happens to the voltage there? Right, its sign flips from positive to negative, from negative to positive. So I had to pick the right reaction. And then the easy part with these is you just take the voltages and you add them together. But we had to multiply that one by 2. We had to divide that one by 3. Don't care. The voltage does not change except for its sign. Its sign can flip, but not its value. Its sign can flip, but not its actual value. And that part really messes with people, because this reaction and this reaction are only half balanced. This has 5 electrons, this has 2 electrons. What needs to happen to those two reactions to finish balancing them? I said finish. Or finis. I don't know what I said. I can't even say it wrong again. This has 5, this has 2. What should I multiply this reaction by? What's the least common multiple of 5 and 2? 10. So you multiply this by 2 to get the electrons to 10, and this one by 5. And then they both have 10 electrons, and you can merge them together. Does that do anything to these? No. Because we're talking about the potential of a metal. It still has the same potential because it's still the same metal. Oh, let me get you your test. All right, we've talked about nature while you were gone. 3A and B, there's lots of giggling today. Why are we recording right now? All right, evidently someone's released nitrous oxide into the room. A and B, A and B both have the permanganate reaction, so I did not rewrite this reaction down here. They both have this permanganate ion becoming manganese. I decided to just save some ink and not rewrite it. However, the second one has not iodine, you idiot, fluorine. Fluorine losing 2 electrons. Do you feel like that's a legit thing that's going to happen easily? Does fluorine give up its electrons easily? No, it steals electrons, doesn't it? So the way this reaction is written, that voltage is very low. There's not a lot of potential that that's going to occur. It is possible, but you would have to, we'll talk about how it's possible in a little bit. I don't want to get into that yet. So when I add the manganese reaction and the fluorine reaction together, my combined voltage is negative. That is a battery fail. That means that battery is not going to occur that way. The reaction will not move the direction it's written, but it might move in the reverse. If you had all of those components mixed in the proper molarities and everything, it could go backwards. And I regularly see kids, they get their voltmeter, they switch it over to voltage, they connect the battery. There we go, let's connect the battery. And they get the voltage. What's the voltage? Okay. And then if they put the leads on backwards, guess what's going to happen? A big negative sign, right? Because the way it's connected, it's running through the voltmeter backwards, and so we're getting the negative voltage. This reaction, the way it's written, should not flow that direction, should flow the other direction. Yes? All right, more of the same. You add the voltages together. Make sure you flip around the reactions properly. After being flipped around, we got a negative value here. So the answer is no. Hydrogen is not capable of oxidizing copper. Is iron capable of oxidizing iodine? Write the two reactions. They both are negative. The total voltage is negative. That's definitely a no. Right? The voltage needs to be positive for a successful reaction. And then in C, is H2 capable of reducing silver? Write the reactions very carefully. Silver is a plus 8.8. Hydrogen's a 0. So yes, that one should be successful. All right, now to the kind of the meat of the matter. Drawing, figuring out which way the electrons are flowing, and indicating voltage. This is probably on every single AP exam, there's a question like this in the free response. Every single time there's one battery, and there's always some issue with the battery. One common issue is they leave out the salt bridge. The salt bridge is this KNO3 tube that connects the two beakers. One year, they had a break in the wire. So the wire didn't actually connect, and they said, hey, why won't electricity flow in this battery? What could you do to make it flow? And it was like, close the switch. Because if the switch is open, then electrons can't move through the wire. How do I know which way the electrons are moving? Well, you have to pull the voltages. These values should be given to you. They would both be written as reduction reactions. So the magnesium one actually would have been written like this. And then they would have given you a negative 2.37. So you have the copper and the magnesium, and you have to figure out which reaction to flip. Well, when you connect the wires, the electrons are going to flow, so the total voltage is positive. If I flip this reaction, I'll have a negative and a negative, so the total voltage would be negative. That would be flipping the wrong reaction. By flipping the magnesium, I have a positive voltage and a positive voltage, so the cell potential is set upright. Therefore, which metal is losing electrons? Look at these two reactions. Which metal is losing electrons? Magnesium's going to +2. Copper's coming from +2 to 0. So the magnesium's the one giving off the electrons. So the piece of magnesium metal would be losing electrons through the wire. Those electrons would come through this piece of copper right into here. And then this copper ion is going to get the 2 electrons and turn back into a solid. On the other side, when the magnesium loses electrons, it's going to go into the solution and become magnesium ions. The salt bridge has to balance things out. If the negatives are flowing through the wire this way, then positives, you see the little positive I tried to write there, positive ions are going to come out of this side of the salt bridge, negative ions are going to come out of this side of the salt bridge. And then I made the line structure there. This side is always the anode. Anode's where you're losing electrons, and the cathode is where you're gaining electrons. Do you remember the silly phrase we have for remembering which side is which? A Leo cat gers. It's not the best phrase ever, but it kind of flows-ish, like electrons. Okay. Oh, look. Click to anti-spyware. Go away. Thank you. Now they know on the internet that I need to update my spyware. That's not good. All right. Same thing in the second reaction. I had to figure out which one to flip around. Turns out I was flipping around the calcium reaction, so I get a positive voltage. 4.26 volts. That's a high voltage. You don't always put the anode on the left in the drawings. That's just by coincidence here. But in the line notation, the anode is always on the left and the cathode is always on the right. So you have the Leo and then the Ger going on in line notation. That double line that separates them is supposed to represent the salt bridge that kind of connects the two cells. So like I was saying, when you guys get to the AP test in like less than 2 weeks, right? Usually question 2 or question 3 is one entire free response question about electrochemistry. They show a picture of the battery, they give you a reaction, you have to describe maybe what's going on in one of the cells. Maybe you have to describe that this calcium is losing electrons and the calcium dissolves into the solution. Or on the other side, that the gold is gaining electrons, the gold's coming out of solution, something like that. What else might they ask you? If either one of these had a color, they might talk about how does the color of the solution change. So in our reaction, we had this copper solution that was blue, Well, as the ions come in and out of water, that color is going to get either deeper or lighter. So if you're getting more ions, it get darker. If you're fewer, it get lighter. All right. When we got to C, we get to worksheet C, things get a bit hairier. There's a lot of nasty math that we're actually not doing. Let me write an equation down real quickly. So this is an equation we're not actually using for the math. But it does explain a little bit from a Le Chatelier's principle. Le Chatelier was about reaction shifting. You add too many reactants. It's not at equilibrium. It's got to get back there. So first let's look at the two reactions. Why did I pick silver to flip around? We have negative 0.8 and positive 1.78. Why did I flip around the negative 0.8? If I flip around the other one, what would happen to the total voltage? It would be negative. Thank you for saying that as quiet as possible. Yeah. So we'd have a negative and a negative. So you have to switch around so the total's positive. Flip the silver around, and then I have the positive 0.8 and a positive 1.78. Add those together. And that's the cell potential. That's the cell potential if it's a perfect battery cell. That's 1 molar, 25 degrees Celsius, 1 atmosphere. Yes? Yeah. Yeah. When we build our batteries next class in our lab, you guys, I think, are supposed to get like 1.3 volts for that battery. And a lot of people get like 1.1 or 1.3. And it's usually they've done the molarities wrong. They didn't make the solutions very well, or the temperature's off in the classroom, yada, yada, yada. Or some people use tap water, which completely contaminates the solutions they're making, instead of distilled water. If you don't use distilled water, or if you don't have a 1 molar solution, everything gets messed up. However, before we do that, let's imagine that you plug in 1 into each of these spots. I've taken this reaction and I did the products over the reactants. Why is there a 1 there and a 1 there? What would we do for water? In an equilibrium expression, water gets replaced with a 1. And then this is silver, the metal, which is a solid. So I also replace that with a 1. Now, if it's at standard conditions, the molarity for standard conditions is 1 molar. Somebody do the math real quick. If you plug in 1 molar into all of those values, what is 17 is wrong, sir. You are an embarrassment. No. 1 squared, 1, 1, 1, 1, 1, all 1s, we'd have a value of 1. Now, here's the math that goes a little harder. Plug that value in here. What's the log of Q then? What's the log of 1? 0 times 0.59 over N. E cell minus 0. So therefore, the standard cell equals the cell you made. So that equation is about figuring out the voltage for when you don't have a standard cell. And in part B, they are giving you a weird cell. It's not all 1 molar. Did they increase the reactants or the products? She's right. They increased the reactants. If you increase the reactants, answer this from Le Chatelier's principle, which way should the reaction shift? By adding more reactants, it should be more likely to head to the products, right? The potential just grew to go to the products, didn't it? The potential is commonly measured in voltage. So, since they've increased the reactants, the voltage increases. You don't need to do the math. You kind of apply Le Chatelier's principles instead. We don't actually ask you to do the math. In part C, they increase the products and decrease the reactants, so you would see the potential decrease. So I'm going to come back to my battery here. Why is this 9-volt battery only 7 volts? It doesn't suck. It was good. It's old. It's been used. Shreyas isn't the first one that's tested it. It's been wiped off. It's okay. All right. Hasn't been a salmonella recall on these batteries yet. It was what, eggs and lettuce this week? Right. Come on. It's been discharged, and the reaction's been going that way. The reactants, every time it gets used, slowly disappear, and products start to appear. And as they shift that way, its potential decreases. Is it at equilibrium yet? If Shreyas tests this one, does it still have some potential? Yeah. So it's not at equilibrium yet. What would happen if the battery was at equilibrium and he put it on his tongue? Nothing. He'd be like, this one doesn't work. Right? That's how I clean it. Just do it like that. Well, it's very sanitary. So here's the same idea. Going through the math just to prove it. I am not going to ask you to do that math, nor is anyone else. The Nernst equation is beyond what we do. Not that you couldn't do it, but the Nernst equation allows you to calculate the cell potential at weird molarities. Does it surprise you, since the reactants are higher than 1, that the potential went from 2 to 2.1? It went up a little bit. If you add more reactants, shouldn't the potential of the reaction increase? That's what this says. Did it increase a lot? No. Even though they went from 1 to 4.5 and 1 to 4.5, the voltage barely went up because that's a log scale. You have to have a huge increase in the molarities to really get a voltage change. Most of our batteries are actually made with paste solution, so they're super high concentrated so that they can maximize the voltage. Because they've got the ions in a super concentrated form, and that means these molarities are very high. And so the log you're taking here, you take a log of a very, well, that's actually 1 divided by a very big number. Yeah, so you go small value and then adds to it instead of subtracts to it. Yes, yeah. So it's almost solid. It's like a really thick paste. A, very easy. Which one should I flip around? You flipped around the iron one. Nope, flipped around the zinc one, so the voltage would be positive. Then we have a delta G value. This is that same cell potential, just plugged in. F is called Faraday's constant. It's 96,500, or more importantly, on the equation sheet. And N is the electrons. How did I know there were 2 electrons in that reaction? Now up here these are both 2. It's going from zinc to zinc plus 2. There's 2 electrons exchanging hands. So we calculate the delta G value. You could also calculate the equilibrium constant. Look at the value of that stupid equilibrium constant. Which side is favored in this equilibrium? By a little bit? By an insane amount, right? 6 times 10 to the 10th, it heavily favors the products. Most of the reactions we use in batteries heavily favor the products, but we've trapped them in a state of the reactants until we connect the wire, and then it can flow. But even then, don't you every once in a while open up the back of your remote control and it's like exploded on the inside? Because eventually those reactants that are stored are eating through the metal that they're stored in, and they escape, and then they start to destroy your calculator or your whatever, right? Your ray gun or whatever you're using. No? Okay. I decided not to do C. You would just plug it in there, but we don't do that math. We're going to instead just infer, should the voltage go up or down? Zinc, is that a reactant or a product? Zinc ions are a product. Iron, is that a reactant or a product? That's a reactant. They have decreased the iron a whole lot, haven't they? What would happen to a reaction if you decrease the reactants? Yeah, it wouldn't shift to the right, would it? It'd be more likely to shift to the left. So you would expect the potential to go down, to decrease. Instead of having the potential go up by adding a reactant, you've got more products. You're expecting the potential to drop. And I think that's the same thing we're doing in this one. I decided which one to flip around, calculated the voltage, and then I looked at all of the values. We have this for the reactants, 0.3 and 0.2 from the data up here, 2 molar for the product. We have a whole lot of product, so we're expecting a decrease in the voltage because there's so much more product than reactant. And then I set up the calculation for delta G, but it looks like I failed to finish it. That's sad. Cool? All right. At the end of the notes the other day, we kind of like hit this and ignored it. I think I probably said the lame joke like I equal QT. It's actually I equals Q over T. I is the current, which also sounds like some weird I equal current. I don't know, that just sounds very odd. Current is how fast it's flowing. Well, what do we measure when we say flow? What is flowing? Electrons. And they're measuring the charge flowing by, the electron charge flowing by, and they usually say amps. 2 amps, 4 amps. A circuit breaker might be 15 amps. That's a lot of electrons flowing by per second, 15 amps. Another way to say amps is coulombs per second. 2 amps is 2 coulombs per second. So we have the amps and we have the time, so we can figure out the charge. And then there's some unit manipulation going on there to get to moles and then to molar mass. I don't typically emphasize this because it's just a bunch of unit manipulation, and I don't think I've ever seen a question on the AP exam about it. And at this point in the year, I'm usually like worried about that. So I don't usually emphasize this. Welcome back. I would, however, like to discuss this because we didn't talk about it. Let's compare this amazing picture all right. So, for her birthday, someone has gotten Asha some molten salt. This is liquid sodium chloride. Not aqueous, molten. What's the difference between aqueous and molten? Aqueous is dissolved in water. Molten means it's been melted down. It is like lava, but not. All right? So this is some sort of salt in liquid form. Awesome and frightening. You are attaching a strong battery with 2 leads down into there. That strong battery is going to push electrons in from one side, pull electrons out from the other side. So you've connected your battery and then put it on there. Those electrons are going to flow in. Are they going to hit these ions in the molten salt? Yeah. One side's going to pull electrons. Can it pull electrons from the sodium or the chlorine? Can the battery... I see you. Do you see me? Can the sodium or the chlorine give up electrons? Which one can give up electrons? Let's go to the periodic table. What's the charge of sodium? What's the charge of chlorine? Sodium has already lost one. Chlorine has one. Which will the battery take an electron from? The sodium that doesn't have one or the chlorine that does? I know that was a very leading question, but that's what's going on. This sodium's already lost an electron. It can't lose the next one. The next one's in its core shell. It's not a valence electron. It's in a core electron. And the core electrons are held a lot tighter. So you can't pull it off the sodium. You've got to pull it off the chlorine. On the other end, this electron would be delivered into the solution. Would the sodium or the chlorine over here gain the electron? Which of these could gain an electron? The sodium could. Because on this side of the flask, the chlorine already has an electron, but the sodium doesn't. So we see chlorine losing electrons on one side and sodium gaining them on the other. So here we have, at the anode, the bromine is losing electrons. At the cathode, the nickel is gaining them, etc., etc. I'm going to give you guys a second to look at that. I'm actually going to try to set something up while you take a look at that.